Yes, obviously I will. That's the job.
Why is Adam a bastard?
Must we ask questions?
I'll ask you guys questions.
Must we answer?
That would be necessary, yeah.
Okay.
Do I need to bring out a calculator for this?
Yes, you will need a calculator for this. But it's a simple question, so it's nothing complicated, but yeah. Okay, I'm gonna start now.
Okay. There's only us two.
I can wait for one more. There's others supposed to come, but I can just start.
I'll tell
Let's wait.
them.
Okay, let's wait till 6:45 and then we'll start.
Okay.
When you say when I start, you just turn off your mic and all, and then when I ask you a question, you turn it back on.
Yeah.
Okay.
I think my calculator's dead.
It's fine. Maybe Adam then will have a calculator or something.
Yeah, I have a calculator on me.
Okay.
I'll just answer. But the answers is there in the corner.
Is it? Yeah, but you still need to figure out
But
how to.
I'll ask questions like it's not always going to be calculations. Like you will have to answer like one or two theory questions maybe.
Wait, so what questions are you gonna ask? You might as well tell us now.
No, you have to wait.
Yo, you actually want to teach
You
us,
go to
yeah?
the real class.
Yeah. Is there any more people?
I wonder why Wade isn't joining. Saying he's fighting Signal, yeah.
Oh, that's right. Um, just one more minute and then we can just start.
Where's Lorenzo then?
I have no idea.
He's very quiet on the group chat nowadays, yeah.
Okay, let's start. Good afternoon, class. My name is Azhar Toffar. I will be wait, am I recording? Hold on. Yes, I am. Okay. So today we'll be doing angular motion. I will be a tutor for this afternoon. But before we tackle the example, I just want to know from all the students in your own words, what your definition of angular motion is without checking Google. You can use the chat, you can turn on your mic, whatever you want to do.
I think angular.
Nah, go on.
I think angular motion is got to do with not like circular motion, like motion that's going in a circle, not circle, but around a point. That's what I think it is.
I
Okay.
think it's motion that rotates around a fixed point or something like that. It just rotates, yeah.
Okay, well, according to Google, angular motion is the motion where an object slash body moves along a curved path at a consistent and constant angular velocity. So that is what, so your definitions are valid, but you just have to go more in detail. Okay. So when it comes to calculations in angular motion, we know that the equations of motion are used to determine velocity, acceleration, and displacement in linear circumstances, right? Now, the same thing occurs in angular motion. Now, in angular motion, the equations of motion are essentially the same, with the key difference that each variable is different. So, for example, linear velocity will be converted to angular velocity, and it will be represented by omega measured in radians per second squared. Radians per second. And the linear acceleration will become angular acceleration, and it will be represented by alpha measured in radians per second squared. And for displacement, linear displacement will be converted to angular displacement, also known as arc length, and it will be represented by theta measured in radians. And when it comes to time, it doesn't matter whether it's linear or angular motion, because time in both circumstances is constant. Okay. So as you can see by the formulas here, it's exactly the same in equations of motion for linear traversal, with the exception that the variables are different. And if you, and also another term for linear motion is translational motion, because it follows a linear path. It translates a linear path. Okay. So when it comes to converting from one form to another, we use the distance from the reference of an object that is rotating or moving along the curved path. In this case, it will be the radius. Okay. So for displacement, in order to convert linear displacement into angular displacement, we have to divide it by the radians or the reference distance. Okay, and the same applies for every other variable concerning linear motion. In order to convert that into angular motion, is to divide it by the radius, or vice versa, timesing it by the radius to get linear motion. Okay, and of course, time remains constant. So if you can take a look at the example here, what we have here is a coin with a diameter of 2.82 centimeters dropped onto a horizontal surface. The coin starts out with an initial angular speed of 12.5 radians per second and rolls in a straight line without slipping. If the rotation slows with the angular deceleration of magnitude 1.8 radians per second squared, how far does the coin roll before coming to rest? Okay, so I would like to ask you, the students, as engineers, if you are presented with a problem like this, what is the first thing you would do before solving it? What's the first thing you do when you see a problem like this? Anybody?
I'll check what variables I have and what I'm looking for.
Okay, so what you're basically saying is that you write down the variables they give you, correct? Okay, so if you go through the question, we can see that the coin has a diameter of 2.82 centimeters. Okay, so they give us that. So you would write this down. Excuse my handwriting. I've never written on PC before. And you would obviously convert this to meters, because that's the standard unit of measurement for displacement, which would be 0.0 divided by 10, I think, or 100, you get 0.0282 meters. Okay. And we can go further on. It's dropped onto a horizontal surface, so it's moving on a linear path, but it's rotating. The coin starts out with an initial angular speed of 12.5 radians per second. Initial angular speed of 12.5 radians per second. So we said earlier that angular speed is represented by omega. Okay. And since it's initial, we would indicate that with an I. And we say that's equal to 12.5 radians per second. Okay. So we have that. We say it rolls in a straight line, of course, and without slipping. Now, I want to ask the students, first of all, what does without slipping mean? And how does it affect the question? How does it affect our working out and our answer? Can anybody tell me?
Sorry, can you repeat the question again?
So okay, first of all, what does without slipping mean in a question like this? Let's start off with that.
Doesn't mean without friction.
It means, okay, Zaire, do you want to give it a shot before I?
Doesn't mean there's no resistance from the surface.
Okay, so the coin is, when it says without slipping, what it essentially means is that the coin is not sliding across the ground, which means the velocity at its base is 0. Okay, so if I were to draw this out, right, we have a horizontal surface. Then we have the coin that's rolling. Okay, so when a coin is rolling, when it says without slipping, what it basically means is that the point at its base that is in contact with the ground, its linear velocity is 0. Okay, v equals 0 at that point. Okay, so what does that mean? It means that every point along this as it rolls is 0, right? So it uses those points as pivot points to push itself forward as it rolls. Okay, so with that in mind, we can say that the translational or linear kinetic energy is directly proportional to the angular kinetic energy, which means the linear center mass speed. So since we know that along the curve, the velocity is equal 0 at the base, right? We know that as it rolls, its center mass has a velocity, right? That is the linear velocity that we take as a reference when we calculating a question like this. Okay, so we call this VCM. Okay, and obviously you have your angular velocity, right? So from this we can say that, like we said, the translational kinetic energy is directly proportional to the angular kinetic energy, which means that in the angular kinetic energy formula, we have both speeds with the I represented for inertia, as well as the um, mass for the translational kinetic energy, right? So from that two equations, we can assume that, or we know that angular speed is not equal, sorry, it's directly proportional to the linear speed, right? So it's directly proportional center mass. So if angular acceleration, angular speed increases, the linear center mass velocity also increases when an object has no slip. So if you didn't know that, now you know. You can use that logic, that level of thinking in an equation that concerns angular motion. Okay, so and from our previous slides, we can also say that the linear velocity, in this case, it is the linear velocity of the center mass, is equal to the angular speed times the radius. Okay, that is the equation that we used or that we found out in the previous slide. Okay, so we can move on. So I hope everyone understands what without slipping means. If not, you can ask questions, whatever. Okay. So as we proceed on, if the rotation slows with an angular deceleration of magnitude 1.86 radians per second squared. So we know that angular decelerate or acceleration is represented by alpha. Okay. And since it's deceleration, we can indicate this with a negative sign because the object is decelerating. Okay. So we have, okay. So we have the angular deceleration. Okay. Now the question is, how far does the coin roll before coming to rest? So we know when they talk about distance in this manner, okay, when they say how far something is, they always refer to the linear displacement. Okay. When they talk about how far something is, right? But if you look at our variables, we actually don't have any linear motion variables. All we have is the initial angular speed and the deceleration of the coin. Okay. But if you look at our formulas, I would like to know which of the formulas should we use from the students? What do you think is the right formula to use in this case? Without complicating it too much. We just need one formula, not two or three, just one.
I think the last formula on the angular motion side.
Okay, this one.
Yeah, that one.
Okay, so let's check if we should use that. Okay, so what did they give us? They give us the initial angular velocity. So we can sub that in there. And they give us the angular deceleration. We can sub that in there. Okay. But, oh, and I forgot to write this. They said that how far does the coin roll before coming to rest? Okay. So that from that we know that the final angular velocity is 0. Okay. So we can sub that into that formula. Okay. And oh, we don't have this though. So in a case like this, when you talk about displacement, okay, since we have mostly angular motion related variables, we first have to find the angular displacement before we find the linear displacement, because that's the only type of displacement we can find at the moment. Okay. So with that knowledge, we know that this formula is indeed the right formula that we can use, because we first have to find this variable and convert that into linear displacement. Okay. So if we write it out, we have final angular squared minus initial angular squared is equal to 2 alpha times theta. Okay. So we can sub it in. So we know that 0 squared is 0. You know that 12.5 squared. Can anybody do that for me?
Yeah. 156,25.
Okay, 156,25. Oh, and when we're done with this question, we're going to check our answer if it's right. Okay, so if the values you are giving me is wrong, then we're going to do it again. Now we sub in the deceleration, which is negative 1.86. And our objective is finding theta. Okay. So can anybody give me what theta is equal to?
I got 42.
Okay, 42. Just 42, or is there more to it?
42.002.
Okay. And this is measured in a radians because it's angular displacement. Okay. And now, so what is the next step? Can anybody tell me what the next step is from our previous equations?
We must convert it to translational displacement.
Okay, and how do we do that?
You multiply by the radius.
Okay, so we times 42 by the radius, which is 0.0282 divided by 2, which gives us anybody besides Mr. Jappi?
Can I see the formula again?
Sure. Sorry.
The answer I got was 1.184.
1.184. Let's check. 0.0282 divided by 2 is okay. Oh, what are you calculating? Are you calculating the radius? Oh, sorry, not the yeah, the radius. Sorry, because I get for the radius I get 0.0141.
I used the wrong value in my calculation. I'm sorry.
Oh, okay,
So, but I got that answer after I changed the value.
okay. So yes, in questions like this, you should always be careful of not using the wrong um, conversions or the wrong values, you know, because it'll mess up your entire um, working out. Okay. So here, oh sorry, I already calculated there. So that is our radius. Okay. And now we can calculate the translational um, displacement. Okay, so can anybody remind me what the formula is? I'm not going to go back. I want to see if you guys remember.
It's the radius multiplied by the angular velocity.
Okay, so we have S is equal to theta times radius. Okay, so we said that our theta is 42. It's basically 42 because it's 0,002. So we just leave it 42. And our radius is 0.0141. Can anybody give me the answer?
The answer is 0.592.
Okay, so that is, we'll check now if it's right. 2. And yes, we do get 0.592. So that concludes this tutorial session. We will examine more examples in later tutorials, but until then, class is dismissed. Thank you.
Thank you, sir.
Thank you.